Hi everyone, welcome back to another physics webinar. Today's webinar is going to be on moments, equilibrium and the parallelogram of forces. So we're carrying on with the forces topic. We've already done 3 webinars on it, and this is just building on what we've already learned. So this session will be 1 hour long as usual, and it will be recorded and it will be uploaded onto YouTube later so that you can refresh, revise and get down any notes that you might not have got down in this session. If you don't know me already, my name is Preshayla. I study physics at Loughborough University and it's my 4th year as a tutor. What we're going to cover today then is we're going to talk about this idea of suspended equilibrium and the centre of mass. So we're going to continue to build on that idea that we touched on yesterday. We're going to go over gears again because I think that it can be quite a complicated topic at first, and I want us to go through a worked example so that we can really see the relevance of them. Then we're going to talk about the principle of moments again. I know you guys are probably sick of it by now, but it is the most common question that we get in the GCSE. Then we'll talk about the parallelogram of forces, and we'll do some exam questions, maybe a little quiz and some questions that you guys that I've not already answered. Okay, so let's start by talking about what we covered yesterday. So we talked about levers and gears acting as this thing called a force multiplier. Now a force multiplier is this idea of us putting in a small amount of force and letting the levers or the gears do the work for us and create a bigger force. So for example, what we saw yesterday was the girl trying to lift up a rock by using a plank of wood. And what we saw is that the girl was pushing down on the plank of wood, which allowed a big force to be lifting the rock. So she put a small force in, which created a big force so that she was able to lift the rock. So force multipliers are really useful. There's loads of applications in real life, and levers and gears are just 2 examples of them. What else we looked at was gears, and we said that a high turning effect or a high moment results in a low speed, and low turning effect or moment results in a high speed. Then we finally looked at the centre of mass and saying that it's the point at which the mass is concentrated or equally distributed, or where the weight acts. It's not really a real point. It doesn't really exist. It's a virtual point that physicists use for calculations and to show that that is where the weight of the object acts. Okay, so the first thing that we're going to look at today is this idea of suspended equilibrium. And what this means is that if you suspend an object, so it could be on a wire, a cable, as you can see here, it's through some strings hanging from a frame. As we saw yesterday in the sine example, we just had a little kind of flagpole thing and our sign was hanging off there. Any which way an object is suspended, it will always come to rest with its centre of mass directly below its point of suspension. Quite wordy. Now what that really means is that if we hang an object, let's say it's our flower basket here, and that flower basket starts to swing for whatever reason, it might be the wind, it might be that we've touched it, starts to swing, okay? Now we know that anything that swings naturally will always come to rest because of air resistance. Now it comes to rest at a special point. And that point is special because the centre of mass of the object is directly below the point of suspension. So in this example, the point of suspension is this, that is where we're hanging the flower basket from. And when it comes to rest, so on the left, its centre of mass is directly below its point of suspension. And this is what we call suspended equilibrium. Suspended equilibrium is that when you suspend an object, it will come to rest with its center of mass directly below the point of suspension. And we can have that in loads of different examples. So for example, you might have a dangling light switch. So you know the ones that you pull, those are in suspended equilibrium. So you pull it and then it swings around for a bit, and then eventually it comes to rest. And when it is at rest, it's in suspended equilibrium. And the center of mass of the little knob that's on the end is directly below the point of suspension, so where your light switch is being hung from. And we see this all around us: chandeliers, flower baskets, signs, lights that hang from cables, bungee cords, loads of things. Okay, so that's all suspended equilibrium is. On the left here, I've just given us a little reminder of what the center of mass would be for a regular shape. So on the left, we've got a regular rectangle, and on the right, we've got a regular triangle. And we know that for regular shapes, the center of mass is just directly in the center. And for irregular shapes, we need to do this experiment. So this is an experiment that I explained yesterday. And what it is finding the center of mass of an irregular shape. And so you can see that the irregular shape that we've got on our clamp stand here is sort of like a trapezium, sort of, but a bit irregular, and we don't know where the center of mass is. So what we do is we punch a few holes in it and we put them in the corners. And then we hang our piece of card with each hole in turn. So the first hole that we might do is this one here, and we hang it with that hole. And then what we also have is this thing called a plumb line. Now a plumb line is simply a string that we also hang from the same clamp with a bob on the end, or a small weight on the end. And what that does is allows us to trace that line of the string onto our card. Okay, so we're going to trace this straight line of our pendulum or our plumb line onto the card. And what you see is that it goes vertically downwards from the hole. Then we do the same thing with our next hole, and so on and so forth until we've got a bunch of lines. Then we're going to take everything off the clamp stand and put our card on the table. And we're going to see where all of those lines meet. We might do 2, we might be 3. Where do those lines meet? That point of intersection here is known as the center of mass. So now we found the center of mass for that card. And what's important to remember is that it doesn't matter which way the card hangs. The center of mass is always in the same position. Okay, so let's quickly go over gears again, because I want this to be really clear for you guys. So what we do when we change gears to a low gear is that a small gear wheel is driven by the engine shaft and is used to turn a larger gear wheel. So that's the first key bit of information that you need to know for a low gear. The small gear wheel is driven by a larger gear wheel. And then the second key bit of information that you need to know is that the output shaft turns slower than the engine shaft. Okay, so this output shaft is turning slower than the engine shaft. And the third key bit of information that you need to know is that the turning effect, or the moment, remember they're exactly the same thing, of the output shaft is greater than the turning effect of the engine shaft. So what that means is that the moment of the output shaft is greater than the moment of the engine shaft. Now this results in a low speed. For high gears, it's exactly the opposite. A larger gear wheel drives a smaller gear wheel. Larger gear wheel drives a smaller gear wheel, and the larger gear wheel is on the engine shaft and the smaller gear wheel is on the output shaft. And this time the output shaft turns faster than the engine shaft. The output shaft turns faster than the engine shaft. And the turning effect of the output shaft is less than the turning effect of the engine shaft. So what that means is that the moment of the output is less than the moment of the engine shafts. Okay, so for me, this whole idea of gears is probably best memorized. So just remembering for low gear, the conditions, and high gear, the conditions. So those 3 bits of key information that we need to know and that we need to remember. Okay, so let's go through a worked example. This is kind of an example of an exam question you might get in your GCSE, but as I said yesterday, these aren't very common. So for this, we have a gear wheel of radius 20 millimeters, which is used to turn another gear wheel of radius 10 millimeters. So you might want to draw a diagram, and the diagram is going to look something like this. We've got a larger gear wheel, which is being used to turn a smaller gear wheel. Okay, and those gear wheels are in contact. Now the radius of our larger gear wheel is 20 millimeters. And the radius of our smaller gear wheel is 10. And it does this with a force of 80 newtons. Now it wants us to calculate the moment of the force on the 10 millimeter wheel and the 20 millimeter wheel. Now the pivot for a gear is in the center. Okay. And the radius is, as we know, the distance from the center to the edge. The perpendicular distance of the line of action of the force on each gear wheel is equal to the radius of the gear wheel. So what that means is, in our definition for moments, we know as moments equals force times perpendicular distance to the pivot. So what that means is the radius of the gear wheel is the perpendicular distance to the pivot, which we can see. This represents our radius here. And our pivot is that dot in the middle. So you can see that it's a perpendicular distance from the pivot. So the radius represents our perpendicular distance. Okay. Now we know that moment equals force times distance. And in this case, our distance is our radius. So the moment for our 10 millimeter gear wheel is moment equals force, 80 newtons, times radius. And remember, we need to put our radius into meters. So we're going to do 10 divided by 1,000. And when we times that all together, we get 0.8 Newton meters. NM, Newton meters, is the unit for a moment. And we can do exactly the same thing with the other gear wheel. So the other gear wheel is 20 millimeters. And what we learned yesterday is that they exert equal and opposite forces on each other. And if they exert equal and opposite forces on each other, that means that both of the forces are equal to 80. And so we can do the exact same calculation again, but this time our distance is 20 millimeters. So we do 80 newtons times by our radius, which is 20, but remember we need to change it into meters, so we do divide by 1,000, and we get our answer as 1.6 Newton meters. And now we found the turning effect, or the moment, for both of our gear wheels. So we can see that the turning effect of the larger gear wheel is bigger than the turning effect of the smaller gear wheel. Okay, so here we have a seesaw, and this is a classic example, classic scenario that they always give in GCSEs of moments. So for the top and the bottom, it's basically both a seesaw. The top shows you the people, and the bottom diagram just shows you the weight. And this is the idea of the principle of moments. And what the principle of moments is that if we have an object which is balanced, the sum of all the clockwise moments equals the sum of all the anti-clockwise moments about the pivot. Okay, so let's draw some arrows to show us that idea. So we can see that our seesaw is in balance. It's not toppling to one side or the other, it's in exact balance. And what the principle of moments says is that about the pivot, the total clockwise moments, so this is the clockwise moments, because if he was to push down, his seesaw side would go down, and therefore we kind of continue that arrow round, and we can say that that's the clockwise moments. And for the girl, we have anti-clockwise moments. So what we say is that the moment on the right, or the clockwise moment, is equal to the moment on the left if it's in balance. And we know that the equation for moments is force times distance. But we have a moment on either side of the pivot. We have the moment of the boy and we have the moment of the girl. So now we have two moments which are equal to each other because the seesaw is in balance. And so we have the moment of the boy and the moment of the girl. So we're going to call this one moment boy and moment girl. And what we know is that they're at different distances and they have different forces, different weights. So we're going to call that force of the boy, distance of the boy, force of the girl, distance of the girl. So all I've done there is put a little letter next to the moment, force, or distance to just show that it's either the boy that we're talking about or the girl. So let's set those moments equal to each other. We know that the moment of the boy must equal the moment of the girl. And so what we end up getting is FB times DB equals F of girl, force of girl, or weight of girl, because that is the force, times the distance of the girl from the pivot. And so what I've done is I've set the top equation equal to the bottom equation, because the moment of the boy, MB, is equal to the moment of the girl, MG. And so now we have a new equation, and this represents the principle of moments. If we have the force of the boy, the distance of the boy from the pivot, and the force of the girl, we can find out the remaining term, which is how far the girl is sitting away from the pivot. So you can see that if we have 3 of these terms, we can find out the other. So if we have 3 of these terms, we can find out the other one, the remaining term. Now, the calculation here that I've just described is not necessary in the AQA syllabus. but you do need to be able to recall the principle of moments and show it in equation term. So using moments, what are they really used for? Why do we care so much about moments? Well, moments, as we've seen, can be used to move heavy loads. So it's this idea of a force multiplier that we've seen in levers being able to move heavy loads. Okay, so we're going to take a quick break, and what we're going to do is a little poll for next week for the new time for large group tutorials. So basically, I'm going to launch a poll on Zoom, and you need to go onto the poll and pick what time suits you for the following, out of the following time slots next week for the online school tutorials to take place. So you can either pick 2 to 3 or 3:30 to 4:30. So I'm going to launch that poll, and hopefully you guys will be able to see it pop up on your screen. So please have a go and vote for which one you would like. It would just help us to plan the sessions better. Okay, 25 out of 29 of you have voted. So I'm just going to see if there's a few more people who can vote. The most rated time right now is 2 to 3 on my screen. So 17 of you have said 2 to 3 and 10 of you have said 3:30 to 4:30. And I believe this is being done in other sessions. So yeah, we'll just take all of the responses and average out what the best response was. Okay, I'm just gonna quickly screenshot that and we can get back to the rest of the content. Okay, so we're going to move on to this idea of the parallelogram of forces. Again, not something that is tested a lot in GCSEs, but it's something that is important. So what it is if we have two tension forces, so let's say in this example, we have a ship and we have two tugboats which are pulling that ship along. One is at this point, tugboat X, and one is at this point, tugboat Y. And the ship moves in the direction of travel, which is forward. So you can see that the direction of travel here is forwards. So that's kind of weird because we've got a tugboat acting diagonally and another tugboat acting diagonally. So it's not really kind of logical that the ship should move forwards. But the reason that it moves forwards is because those two tension forces can be combined into one force known as the resultant force. So it's exactly what we've been doing before, but instead it's known as the parallelogram of forces. So it's still taking forces and combining them into a resultant force. Okay, so this talks about the parallelogram of forces in a different way. We still have the tension in the cables or the wires. Acting outwards. And we have an angle, θ1, between the wire here and the wire acting downwards, and another angle θ2 between the wire here and the wire acting downwards. And we have 3 weights. The tension in each string is equal to the weight that it supports. So the tension on the right-hand side would be weight 2, and the tension on the left-hand side be weight 1, because the tension in the wire is equal to the weight that it supports. The point at which the 3 strings meet is at rest. So this point is at rest, not moving. And a parallelogram can be drawn using the angle so that the line down the centre of the diagram represents the vertical line through the point where the 3 strings meet. And adjacent sides of the parallelogram at θ1 and θ2 to the vertical line, so these lines here, represent the tensions in the string, which we've seen, tension in the string. And so our parallelogram of forces can be drawn by completing the diagram with a single line. And so we have our parallelogram of forces, or rather 2 parallelograms of forces. So let's do a worked example to really understand what this idea is talking about. So here we have a car and it's being towed by a tow rope. And that rope splits into 2 and is attached to 2 points on the car. 1 point is here and 1 point is here. So we have 2 forces, 2 tensional forces, because we have 2 bits of rope which go into 1 rope. So there is some tension in this top wire. So there is some tension in this top wire, and there is some tension in this bottom wire. And those ropes are at a 30-degree angle from each other. Now what we can draw is our parallelogram of forces. So I like to start with the angle, and you'll need to do this with a protractor. So you're going to draw a 30-degree angle, and from one edge of the angle, draw your first force, your first tensional force. And on the other side of the angle, draw your second tensional force. So this represents the tow rope, and these are our tensions. Okay, and so what this shows is that we've got 2 tensional forces acting at 30 degrees to each other. Now what we want to do is combine those 2 tensional forces into 1. And we know that the resultant force is the combination of these 2 tension forces. What we're also told on in the question is that the tension is equal to 3,000 newtons. So we can label the top force with 3,000 newtons and the bottom force with 3,000 newtons, because the tension in each rope is equal to 3,000 newtons. Now you'll notice that we have a scale here, and that is because the parallelogram of forces is a scale vector diagram. And if you're drawing it in an exam, you must put your scale. In this example, they've used 1 centimetre equals 1000 newtons. And therefore, this line would be equal to 3 centimetres. And so with this line, because it's 3000 newtons and therefore 3 centimetres. Then you're going to carry on that line. So you're going to draw. So the next step is to draw a red horizontal line going halfway through the tension forces. So it starts at this point here and it's a completely horizontal line. Okay, that's going to represent your resultant force. So you're going to start by drawing this red line and extending it out. Then you're going to draw 2 dashed lines from each tensional force. And the point at which they meet is the point at which the resultant force stops. Then you're going to measure the length of that resultant force. And whatever the length of the resultant force is, you're going to use your scale to convert it into newtons. So I'll go through the steps again. First of all, you draw your angle. Second of all, you draw your tension forces. So you're going to draw one at the top, one at the bottom. Then you're going to label the tension forces with their value. So in our case, we had each of them equal to 3000 newtons. Then you're going to draw your axis, so your horizontal line from the point at which it's being towed. So it's going to go straight through the middle, and that's going to represent your resultant force. And that extends for, just draw it as long as you can. And then what you're going to do is draw dashed lines from each tension force. And the point at which they meet is where your resultant force will end. Then you measure your resultant force, and the length of your resultant force can be converted back into newtons using your scale. Okay, so that's all the content, and I think we'll finish off that heavy content with a quiz. This is going to cover what we did yesterday and what we did today. So if you could just type in joinmyquiz.com. It's only 9 questions today. And the code will come up on the screen in a second. So you want to type in joinmyquiz.com and 613933. I'm going to put the link on the chat as well for those of you who prefer to access it that way. You can join from your laptop, your smartphone, your computer, your iPad, whatever you're on really. And you don't need to see my screen to do the quiz. Okay, we've got 14 of you in and 25 of us. So I'll wait for a few more. Okay, let's start. And the rest of you, if you haven't managed to join, can join through the link on the Zoom chat. This quiz will require you to remember the conditions for the gears. And so it might be a bit tricky in that way if you've not managed to memorize it yet. That's absolutely fine if you haven't. It does take a while to kind of stick in people's heads. So don't worry if you do get the questions about gears wrong, because it does require memorization. Okay, we've got 4 of you who have got full marks and 74% accuracy, which is really, really good. I'm really impressed with that. Well done, guys. .77% accuracy, that's really good. We push it right up there. And I think that's one of the highest that we've got. So that's really good. Okay, looks like quite a lot of you are done. So I'm gonna move on to the answers. Okay, so levers and gears are of course known as force multipliers, the idea of us putting in a small force and it doing the work for us, and we get a much bigger force out. Gear wheels exert equal and opposite forces on each other when they are in contact. So that's Newton's third law. So they exert equal and opposite forces on each other when they're in contact. For a low gear, the small The larger gear wheel turns a smaller gear wheel, and the output shaft turns faster than the engine shaft. For a high gear, the small gear wheel turns the larger gear wheel, and the output shaft turns slower than the engine shaft. Just things that you need to memorize, really. You might want to come up with a mnemonic to help you remember it, or you might prefer to do it with diagrams, however suits you, really. The center of mass is, of course, the point through which the weight of the object acts. And the principle of moments is the sum of all the clockwise moments equals the sum of all the anti-clockwise moments. The reason that I put the first answer in there is kind of a trick question, because some people think of it as the left moments and the right moments, but that's not quite correct. We must talk about it in terms of clockwise and anti-clockwise. The tension then in each string is equal to the weight that it supports. So the tension is always equal to the weight that it is supporting. Okay, that was a really well done quiz, and we've managed to push it right up to 80% accuracy. I know that you guys always like to know the winners, and so Essie came first, Rabail came second, DL, Summer, Emma. Okay, so well done to all of you who got 4 marks, and well done everyone for getting 80% collectively. Okay, let's try out some, oh, here's the leaderboard. There you go, you guys can see it. Cool. Okay, so let's try out some exam questions for the last 15 minutes. You guys haven't put any questions on the chat, and I just want to remind you that if you do have any questions about anything that we've covered so far in Forces, any exam technique tips, anything like that, please do put them on the Q&A function. Remember, you can submit them anonymously or put them on the chat function. Any questions are fine. I really don't mind answering. It's not like school where, you know, you have to ask questions about the topic that you covered today. Just ask me anything. Yeah, okay, so let's go through some exam questions. This is an exam question about center of mass, and it shows a life belt hanging freely from hook Y. So it's hanging, and what I want you to be thinking about here is that we see the word hanging, and we see the word hanging freely. And so immediately what I want you to think about is suspended equilibrium, that first topic that we went over. When we see the word hanging, and you know, we've got an object hanging from something, we want to be thinking about suspended equilibrium. So going back to the question, let's apply what we've learned. On the diagram, mark with an X the point where you think the center of mass of the life belt would be. Now be really careful here. This is kind of a trick question. Remember the fact that the center of mass is not actually a real point. It's a virtual point, and it can be wherever we want it to be. Where do we think the center of mass of the life belt is? And explain why you choose that point. Really careful here. What do we think? Put your answers in the chat. It is a pretty tricky question, which is why I've chosen it. Okay, so the center of mass is going to act in the center of the object. Okay, this is quite an abstract question, because you really wouldn't expect the centre of mass to be in thin air, right? This is a hole cut out of the middle. And so it's not really kind of logical to think about the centre of mass just being in thin air, and it's not on the object. So this is why I emphasize the point that the centre of mass is a virtual point. It can be anywhere that we want it to be. So the centre of mass, what we learn from this is that the centre of mass does not necessarily need to be on the object. If it's got a hole cut out of the middle, it is in the centre of that hole if we have a regular shape. It's the same thing if we were to take, and I don't really know why you do this example, but if you were to take a photo frame and you were to hang it in the same sort of way, the centre of mass is going to act directly in the centre, although the centre of that photo frame is just thin air. Okay, so what we learn from this is the centre of mass does not need to be in the object. Now, why we choose this point is the fact that all the weight acts from this point. So although it's not on the centre, it's not on the ring, that is where the weight is going to act from, right? It's going to act downwards at this point. That's where we draw the weight. If you ever get stuck on where you think the centre of mass should be, you can imagine doing the experiment that we did before to talk about irregular shapes. So hanging that circle from our clamp stand, putting holes in it, hanging it from the holes, thinking about where those lines would intersect. And what you'll find is it's right in the middle. But you can't really draw the line because the centre is cut out. So another way that you might want to think of it is a solid circle. So doing it with a solid circle, like this. Okay, so think about where the centre of mass would be for a solid circle. Well, we know from earlier that it's just going to be in the centre. Okay, now we cut out a section in the middle. Cutting out a section that is identical to the original shape means that the centre of mass stays where it is. Okay, so that is what that question is me trying to teach you, so that you don't kind of see it for the first time in an exam and think, well, there's no centre of mass because there's just air there. So every object does have a centre of mass, every single object. But what is meant by the centre of mass? How do we define it? If you guys had this question in the exam, how would you define the centre of mass? Have a think. What do you think the centre of mass can be defined as? The point at which So the centre of mass is the point at which the weight acts. Okay, so it's the point at which we can say all the mass is concentrated. Okay, so here we have a boat and a fisherman is pulling that boat towards land. So the land might be over here. So the fisherman is pulling that boat towards the land, and he exerts a force of 300 newtons. So he's pulling with a force of 300 newtons. But the sea is exerting a resistive force of 250 newtons. Now, what do we think happens? This is thinking about resultant forces. What is happening? The forces are clearly unbalanced, and so the resultant force is not zero. What is the resultant force? If it's not zero, what do we think the resultant force might be? Seeing as we have a 300 force going forwards and a 250 force opposing it. Remember, when we have two forces which are unequal but opposite, we subtract. So what do we think the resultant force would be? Put your answers in the chat if you think you know. What would the resultant force be? Okay, so lots of you are saying 50 to the right, and that's absolutely correct. It does go to the land, and it is a resultant force of 50. So we have 50 going forward because that is the resultant force of the 300 newtons going forwards and the 250 newtons opposing it. And therefore, because we have an imbalance in the forces, we have a resultant force. Now remember, a resultant force means that the motion of the boat is changed. And so a 50 Newton force acts on the boat in a direction towards the land. Okay, so the motion of the boat is a constant speed which relates to the force of 50 newtons in a direction towards the land. When two objects interact, they exert forces on each other, but which statement about the forces is correct? This is Newton's third law. When we have two forces, because two objects are interacting. So it says, what are they unequal? Are they equal and in the same direction? Are they unequal in the same direction? Are they equal and opposite, or are they unequal and opposite? What do we think? Okay, you guys are saying the third option, and that's absolutely correct. Equal and opposite, action and reaction, however you want to think about it, they're going to be equal in size and in opposite directions. And that's for lots of things, so such as a box sitting on a table, we have a weight. And remember that that force must have an equal and opposite reaction, and that is known as the normal force, or the reaction force, or the normal reaction force. Okay, so here we've got two concrete mixers. On each diagram, the center of the y-x marks the center of mass of the concrete mixer and its contents. So here the center of mass is this white x, and here it's this white x. Complete the sentence to explain what the center of mass means. Center of mass of a concrete mixer and its contents is just the point at which the mass is concentrated, or at which the weight acts. Now both diagrams are drawn to the same scale, but concrete mixer B is more stable than concrete mixer A. What makes it more stable, do we think? So this concrete mixer is more stable. What do you think makes it more stable? Have a think. What features of the concrete mixer makes it more stable? Okay, so someone has said its base has a larger surface area. That's absolutely correct. So it's spread over a bigger area, and that means that that it is more stable. The fact that it also has wheels makes it more stable, because it can move around, and yeah, there would be the two features that I would say for that. And finally, let's go through this one of levers. So this is talking about pivots and levers, and the spanner is a simple lever. So that's the word that you're going to put in that blank, lever. Spanner is a simple lever, and you use it to produce a bigger turning effect on the bolt. So that's the whole point of having a lever, is to increase the turning effect or the moment. A longer spanner works better, and that is because there is a bigger distance between your force and the pivot. So a longer spanner works better because there's a longer distance between the pivot and the force that you're putting in. Here, there's no distance between the pivot and the force. Here, there's a much bigger distance between the pivot and your force. Okay, so that's how you'd answer that question. So we've gone through quite a few questions today, and as I'm speaking, I'm going to put on some questions for you guys to try at home. Just pause the video and have a go at those questions. As always, this session has been recorded and will be uploaded onto YouTube later so that you can try the questions, refresh, revise, and get down any notes that you want to. Also, if you guys want any kind of one-to-one style tutoring with a tutor like myself, then that is something that MyTutor offer, and you can just go onto our website and go to the Find a Tutor function and find a tutor if that's something that you guys want. So next week, I think that we will be possibly carrying on the topic of forces, and I hope you guys have a nice rest of the week.